Hi, welcome to the second Hitchcock lecture by Professor Peebles. That's Professor Peebles down there. I'm George Smoot. I'm the local, but I'm the person here who probably known him the third longest or the second longest. I don't know if Mark Davis has known him longer or not than I have. But I get the pleasure of introducing him. And yesterday you heard his fairly formal introduction, and you see in the little brochure you got when you came in that he's highly honored in a lot of areas and been a pioneer in the field. But they actually left some of the stuff out that he did that was very influential to me, and I know to Mark Davis and to a number of other people. There's a whole book that they left out called Physical Cosmology, which came out in 1971. And that book was extremely formative to a whole generation of people. And so you look sort of up in the history of cosmology and everything, and you get statements like this. According to many books and surveys of cosmology, including reviews of a more or less historical nature, because it always more or less, right? The field of cosmology only became truly scientific about 1965, primarily as a result of the discovery of the cosmic background radiation, right? And they got sample statements and so forth. To me, I noticed that, but it wasn't. Cosmology didn't really become serious field until I read Jim's first book, because there was the stuff laid out with a huge amount of math, but enough words that I could understand it to know whether it was worth my trouble to learning the math, right? And each of us, Mark learned a certain kind of math, I learned a certain kind of math. And it was that book and the book by Steven Weinberg and a couple of articles by Dennis Sciama, and particularly Jim's book and the articles by Sciama that got me interested in the cosmic microwave background. And the first experiment that we did in that area, we named the ether drift experiment right after the title of your subchapter in the book. And so Jim wasn't remembering how long he's known me, but I stole time out of one of his talks almost 3 decades ago at the American Physical Society meeting in Washington, D.C., which is the big time meeting in those days. And he had an invited talk, and we had new results saying we know that the Earth is moving. Finally, Galileo was right. And he graciously, as he always does, gave up time to this young postdoc who just asked him. Graciously gave up some time so that I could present the results, because it was too late for me to get a talk in the meeting and so forth. And then he's regretted ever since, so he promised to roast me tonight, but we'll see what happens. But I have a couple more things to say about him, and that is you will have seen from his talk how good it is as a public talk and everything. But to physicists, he's what we call elegantly casual. And let me explain that in more detail. He goes and gives these simple, he'll go up to the board, he'll do these simple calculations for you. And they'll be, well, it has to be this bidimensional analysis, or this is a simple calculation. And the answer will come out exactly correct. No factor of 2, no pi, nothing. Just exactly correct. And he does that time after time. And as teachers, we occasionally do that. We don't do Chandrasekhar, we do Landau description and get the limit on the mass of a neutron star, or we do the bending of light by the sun or something like that, bidimensional analysis. And we kind of get the right answer if we fudge it a little bit and so forth. But he does it time after time. And I always wondered, how many nights he spent up doing those calculations correctly to then work out how to do that. Because it's just beautiful to see it come out that way, because you see the physics of what goes on, and that's what's characterized his books, and that's characterized what he's done over this time. And again, he's doing that in these lectures. And so I say the public can appreciate him, the scientists can appreciate him, and there's a lot of us in here and all across the world that came into cosmology because we read your books and we followed your example and so forth. And so it's a pleasure for me to be here and do that. And the only bad thing I can say about you, and you already put it in the biography, is you're a Canadian just like our chancellor. And so, that's like, So rather than take much more time out, because I already owe him some time, let's have Professor Peebles come up here and give the second lecture.
Thank you, George. Friends and colleagues, thank you for coming in out of a beautiful day to this dark room. It's evidence, clearly, that you share our fascination with the world around us. I'd like to begin with a general comment about the nature of this science. Cosmology, the study of the large-scale nature of the universe, is a physical science, and it operates by general rules that are familiar from any other branch of science. You're free to introduce conjectures, postulates, ideas. They should be, and generally are, treated for what they are, just so stories, until they can be tested. A successful test, a prediction that is made and successfully confirmed by measurements, confirms our belief that we're on the right track with this just so story. A failure is a positive step because it tells us we'd better change the story. Continued successes without the need to change the story convinces us we're on the right track to a good approximation to reality. You'll notice that in this description, it clearly follows that there is no absolute truth in physical science, because, after all, we cannot make an experiment that is infinitely accurate. Instead, we are searching for successive approximations. That is why I can stand up here and claim that cosmology at the present day is remarkably successful, even though it has some pretty wild just-so stories buried in it. Okay, so that's going to be my real challenge, to convince you of those two aspects. We have a good approximation to reality, but we have a long way to go. So, to begin, the universe is clumpy on small scales. Here we are, a concentration in a room in the suburban sprawl of the Bay Area, on a planet, around a star, in a galaxy of stars, in the local supergalaxy of galaxies. But the large-scale distribution is somewhat different. You'll notice that in this map, showing the distribution out to a fixed depth of the distribution of galaxies across the sky, there are clumps. I'm going to be drawing your attention in a little while to this particular clump. There are other clumps, and there are wiggles and fascinating texture. But you also notice, I trust, that this part of the world looks a lot like that part of the world. This leads to the first law of cosmology, the first conjecture, if you will. The universe is uniform in the large-scale average, no center, no edge. The second law is that the universe is expanding. Here a description. One observes that the light from distant galaxies is shifted toward the red, as if Doppler shifted by motion of the galaxies away from us. The interpretation of this observation is that the universe is expanding. Here is a two-dimensional illustration of this expanding universe model. I remind you that here we are pretending we live in 2 dimensions, not 3, that you live on the surface of that balloon, and that you agree not to ask me what's off the surface of the balloon. You live on 2 dimensions. Suck it up. That's where you live. The balloon is being blown up. That means that if you sit on a galaxy and look around you, you see the galaxies nearby moving away, and you see more distant galaxies moving away more rapidly. That's the expansion of the universe. Notice that if you go to another galaxy and repeat the measurement, you'll see the same thing. Here is a universe that is uniform, no center, and yet expanding in such a way that everybody sees the galaxies moving away from them as if they were at the center of the universe. But they're not. There is no center. Good. The second law of thermodynamics. Now we come to some conjectures. One may ask, does it not mean that if the universe is expanding, that it's growing less dense than it used to be more dense? Fred Hoyle, on the left here, with Tommy Gold and Herman Bondi, not in the photograph, pointed out that doesn't follow at all. They said, let us introduce a postulate, a just-so story, if you will. Suppose that matter is spontaneously being created at a definite, exceedingly small rate. The newly created matter will, by gravity, pool together in clouds. The clouds may collapse to become galaxies of stars, and these young galaxies will fill the voids that are opening up as the older galaxies move apart. You will thus produce a universe in a steady state, expanding yet not evolving. It's arguably a deeply beautiful idea. Somehow, perhaps for anthropomorphic reasons, it's sort of unnerving to think that our universe is not forever. But I can tell you evidence that it is of compelling interest to many people. Eternal inflation is just a variant of this picture. But But this classical steady-state cosmology has very clearly failed. And here is the reason. Space is filled with radiation with an intensity at each wavelength that follows this curve. It's a very special curve. It is how radiation will relax if sufficiently absorbed and re-radiated so that the radiation can relax to statistical equilibrium, so-called black-body radiation or thermal radiation. This radiation at a temperature of 2.75 degrees above absolute zero. How did this radiation reach this wonderfully characteristic state, characteristic of equilibrium? Surely because the radiation was absorbed and re-emitted many times. But we know the universe as it is now is pretty close to transparent at these wavelengths. You know that because you can see distant galaxies emitting in the radio. The clear inference is that this radiation is a fossil remnant from a time when the expanding universe was dense and hot and able to relax to statistical equilibrium. A fossil, therefore, that is in stark contradiction to the steady-state cosmology. This is wonderful science. A postulate was introduced and demolished. We've made progress. We have now the notion of an expanding universe, and it fits the observation of that radiation. That's good, but of course it's also, in a sense, another just-so story, particularly when you consider that when we look into the details of this theory of the expanding and evolving universe, we need to introduce our own two new just-so stories, that most of the mass of the universe is not in the form of which you and I are made, that you and I are made of material, the jargon is baryons, that occupy only about 5% of the mass of the universe. The rest is in two new hypothetical forms, dark matter and dark energy. Isn't that embarrassing? Absolutely. Does it mean we're on the totally wrong trail? Absolutely not. We're just trying to get successive approximations to reality. So we begin with the dark matter issue. On the right you see Fritz Zwicky, Swiss, many years at Caltech in Southern California, a somewhat irascible figure, but also a deeply intelligent and original astronomer. I spent about 10 years of my life working with the data in this book of the catalog of the nearby galaxies. He predicted the existence of neutron stars as remnants from exploding stars, remnants of supernovae. He predicted that the bending of light by mass concentrations would produce astronomical lenses. I'll show you an example in a minute. And he was the one who pointed out that this cluster of galaxies, which I pointed out to you on the beginning slide, has a curious property. One can measure the relative velocities of the galaxies by looking at the differences of their Doppler shifts. A galaxy moving away from us has its light shifted toward the red, moving toward us, shifted toward the blue. From the observations of those shifts, one can get the velocities of the galaxies in this cluster, and one can also compute the mass seen in the stars, in the galaxies in this cluster, and one sees a distressing inconsistency. Much more mass is required than is observed. The interpretation in those days is missing mass. We've missed some of the mass. We've made great progress. These days we call it dark matter. We still don't know what it is. But we can be very, very sure of one thing. It's not the baryons of which you and I are made. There is no form that could be hidden in there in that amount. There are other examples of this phenomenon. Here is an example of Zwicky's gravitational bending as astronomical lenses. Here is an image of the center of a cluster of galaxies. It's a negative where the image is dark. There are lots of stars. The arc is, in fact, one galaxy in the background, seen in a horribly distorted image. Light from that distant object, which is about in the center of this image, comes toward us at the upper part, moving slightly upward and to the right. But gravity bends it, pulls it over, and directs it to our eye. Light rays coming down from the galaxy slightly and to our right are bent up and over and produce the image on the bottom. Here we see a horribly distorted image of a galaxy. It's a gravitational lens. But what is really striking about this is how smooth that arc is. The bending angle is almost identically the same going around that arc. The bending angle is the same, but the mass distribution in the seen material is wildly inhomogeneous. How in the world could that be? The mass isn't mainly where the stars are. There's a smooth component of mass. Another illustration. Here on the left, an optical image of 3 galaxies. It's a negative again, dark where there are stars. On the right, an image taken with a radio telescope that is sensitive to the light emitted by hydrogen atoms at 21 centimeter wavelength. You see that there's a clear physical connection between these 3 galaxies. They're not just an accidental projection on the sky. They're close and they're doing a dance. But if you add up the mass you see in those 3 galaxies and compare it to the velocity with which they're moving, you see these guys shouldn't be doing a dance at all. They should be flying apart. The standard interpretation, the hypothesis, the just so story is there's a lot of dark matter in there that's holding them together. It's not in the galaxies. It's in the general soup connecting the galaxies. Here's another galaxy, Vera Rubin, at the Carnegie Institutions in Washington, D.C., founded by Andrew Carnegie, the robber baron. But, you know, old dirty money becomes new clean money. He founded the Department of Terrestrial Magnetism. The name hangs on. It's a charming indication of past occupations. Now, this is a world-class center for many branches of science, including astronomy and including Vera Rubin, who measures, in this example, the motion of material in the outskirts of a galaxy. And she finds that this material is moving in a nice circular orbit, part of the disk of the galaxy, but with a disconcerting observation that the material is moving much too rapidly to be held in circular orbit by the seen mass. Again, we need a hypothesis, dark matter. As I said, this dark matter can't be baryons in any known form. Instead, we have ideas that it might be other forms of matter. We have other just so stories. A big effort to check on some of these big just so stories is here collected from some webs, from some posters. The key point, if standard gravity physics is right, and it has passed demanding tests, then matter is not dominated by the baryons you and I and stars and planets are made of. So what is it? One possibility, classes of particles that we interact only very weakly with material of which we are made, but occasionally will hit an atomic nucleus and give it a little kick. So perhaps, if that's the case, you will be able to detect this dark matter. Just take a crystal of material and wait for it to ring, all unexpectedly, because it's been hit by a dark matter particle. Now, you don't do this on the surface of the Earth. Too much radiation floating around. You go deep in a mine that's clean, and you cool the detector down as close to zero as you can get it, and you build a very sophisticated equipment to look for those occasional ringing of the apparatus. Bernard Satelliet is one of the leaders of this operation. I couldn't find him in this picture of co-conspirators.
Upper left.
Upper left. That's not Bernard, is it? Oh. Okay. He doesn't look good in a hard hat. Many of these people do. Most of them are much younger than Bernard, and are very capable, very dedicated, very brave. They're going after a just so story. It'll be wonderful if they have a positive detection. If they get a negative result, that'll be wonderful too. It'll tell us to change our just so story and improve it. This is the best and the brightest. They deserve our support, and we know that no matter how the experiment comes out, they're going to go on to do great things to the world. We must also postulate that about 2/3 of the mass of our universe is in yet something even more bizarre. So here we go, suspension of disbelief required here. Upper left, Albert Einstein. Upper right, Willem de Sitter, a Dutch astronomer, director of the Leiden Observatory. Albert Einstein invented in 15 a new theory of gravity, general relativity theory. He applied it to his notion of a universe that was uniform and found, to his distress, that this universe is inconsistent with his assumption that, of course, the world is forever. That led him to adjust his theory by putting in a new term that he called the cosmic term, that had come to be called for a long time the cosmological constant term, is now called dark energy. You see the great advance in science in that. ever more romantic names. Now, the game is this. Einstein visualized a universe of this sort, but he assumed, it's obvious, the universe is forever. But his theory said, no, this universe will collapse under the force of gravity. Gravity pulls things together. That is a bad thing, it would seem to Einstein, and so he adjusted his theory to put in this cosmic term that acts as a repulsion to push apart the tendency of gravity to draw together. That is the notion of Einstein's universe. The pressure is held in that balloon just such that the pressure, which is the operation of the cosmological constant term, is just such as to balance the attraction force of gravity. It was the Belgian Georges Lemaitre, whose a picture I will show you in a moment, who pointed out that this is an unstable situation. Touch that static universe a little bit and it'll either collapse or expand. By the time he made that point, it was known that the galaxies are moving apart as if the universe was expanding. A brilliant connection made, the universe is expanding. That led to Professor Dr. Willem de Sitter's comment in a Dutch newspaper. You see his shape? It is the Greek letter lambda, which was Einstein's symbol for this new term in his equations. And the quote from the newspaper is, "Whoever blows up the ball, the expanding universe." What makes the universe expand or swell up? That is done by the lambda, Einstein's cosmological constant. Another answer cannot be given. As soon as this point was made, people recognized you don't really need lambda at all. If you're willing to accept that the universe is expanding, then let it expand, and let it do it under gravity alone. Gravity will slow the expansion, but under the right initial conditions, the universe will expand for a long time. Bob's your uncle. We don't need lambda. Here is some correspondence between Einstein and Georges Lemaitre, the Belgian who discovered this connection between the astronomer's observations and Einstein's theory. I was told yesterday I should have made a few comments about that clerical collar. He was an abbé of the Roman Catholic Church. He had absolutely zero problem with the balancing of science and religion. He was deeply influential in the Vatican and respected. He was a deeply influential and original physicist. He, in writings, gave his opinion of how you deal with these two aspects of his work. He said, if you wish to swim, then you would be well advised to do it in ways that believers and non-believers have found to be effective. I would make it more stark and to say that if I decided I'm not going to swim like all of those people who believe in another religion, then there's a distinct possibility I'm soon gone. Isn't that right? And by the same argument, Lemaitre said, if you would do science, then you will do it in the manner that people, believers and unbelievers, have found to be effective. Is that so wrong? To me, perfect science. Here is a correspondence just after the Second World War in which Lemaitre makes the point, we needn't get into the technical details, that Einstein's cosmological term just acts like a distributed energy density, uniformly distributed through space with some peculiar properties. Let's not bother with them. It sets the zero level of energy. Einstein replied with some complimentary works. Thank you for your very kind letter. I doubt that anyone has so carefully studied the cosmological implications of the theory of relativity as you have. He was being nice, but I think he was also being correct and proper in saying that. But then the line I wish to draw your attention to, since I have introduced this term, I had always a bad conscience. Einstein hated the cosmological term. To him, it was an extra appendix that wasn't needed. Other great physicists echoed Einstein's view, in particular Pauli, great Austrian physicist. Einstein was soon aware of these new possibilities, that is to say, get rid of lambda, and completely rejected the cosmological term as superfluous and no longer justified. I fully accept this standpoint of Einstein's, one of the great physicists of all times. A little pompous, but there it is, he meant it. He also had a reason for rejecting it, namely a really ridiculous problem with quantum mechanics. You've heard of zero-point energy. Take two hydrogen atoms, bring them close together, they'll get stuck and make molecular hydrogen. In computing the binding energy, you have to take account of the fact that there is a so-called zero-point energy. Sometimes it's discussed as being a result of the uncertainty principle. You can't make sure that the atoms are really at the center of their potential well and not moving at the same time. The result is a little bit of uncertainty in both that adds up to a little bit of energy. I don't know that I grabbed that. Just live with it. There is zero-point energy in any degree of freedom of motion. The electromagnetic field in quantum physics is a field, and it's also particles, just as particles are fields. Was that somebody? The electromagnetic field is well described by standard quantum mechanics. It has lots and lots of zero-point modes of oscillation that produces an energy density that is ridiculously large, so big as Pauli is recalled as quoting that the energy density in the electromagnetic field, zero-point energy, ought to be so large they will curve space-time so strongly that our universe won't even reach to the moon. It's absurd. His response, we can't live with this, it's not there. This zero-point energy of the electromagnetic field would act as Einstein's cosmic term. Many people recognize this, including Lemaitre, but the person who made it visible to all is Jacob Zeldovich, shown here dancing with his wife at a banquet in Hungary. He started out, like other Russian Soviet physicists, working on the nuclear bomb, was a big factor in the nuclear hydrogen bomb design. Soon sickened of that, turned to physics, just as Sakharov sickened of it and turned to political concerns, social concerns. The consequence was that at the time of this photograph, he was still not allowed to leave the Soviet Union because he knew too much. Not until close to the fall of the Soviet Union was he allowed to get out of the country. Deeply original physicist, and the one who firmly fixed in our mind, you had better learn to live with the dark energy concept because it exists as a possibility. The genie has been let out of the bottle, and it is not easy to force it back in. Well, you can see that we need some help from the observations. We have these hypotheses, we've got to test them and be guided by what is observed. Here is an idea behind the test about our notions of the universe. Recall that Euclid's postulate, or self-evident statement, parallel lines never meet. But that's because Euclid was thinking in flat space. In general relativity theory, space-time can be curved, and that means that lines that start out straight and move in a straight line can cross. That's an effective curvature. You've seen it whenever you peeled an orange, and you've seen the segments with straight lines, each a great circle, coming together and crossing. That has an important effect. Look at the light coming from a distant galaxy. Curvature may do two things. It may bend the light rays as you see in the top illustration or as in the lower illustration. The effect of that curvature is dramatic. In the upper case, the galaxy appears bigger on the sky, so you're gathering more light from it, so it appears much brighter in the sky than in the lower case, where you see you're gathering light from a much smaller cone, and so the galaxy is smaller on the sky and therefore fainter. Those two effects can be tested, of course. Here is Edwin Hubble, a left-hand person, standing in 1931, looking at a projected design for a great new telescope. He and a few others were convinced that it might be possible to look for this effect and to test these ideas about general relativity theory and about the expanding universe, but it would require a big new telescope. It was the 200-inch telescope to be placed on Mount Palomar. Its installation greatly delayed by the Second World War. And I can't just help but pause to remind you This great telescope is still in operation and doing wonderful science. Show me a particle accelerator that was designed in 1931 that's still in use. They're all in the Smithsonian. A dig. Ellen Sandage. 1961, the 200-inch has been completed, commissioned, and is in successful operation. Let us attempt to continue Hubble's great program. Let's look at distant galaxies, measure how bright they are, estimate how far away they are, look for this brightening or dimming due to the curvature of space-time. A bit of data needn't concern us except to point out that along the vertical axis, you are looking at the amount of shift of the light due to the expansion of the universe that I mentioned. Along the horizontal axis, how bright the galaxy is. For reasons that are lost in the mists of time, bright is over here and faint is over here. And the different curves corresponding to different hypotheses about the nature of the universe. So, he made great progress, but he didn't get any definitive answers. Here we are in about the present epoch, late 1980s, early 1990s. Saul Perlmutter at the laboratories just up the hill initiated the Supernova Cosmology project, and with the idea that instead of looking at galaxies, look at stars that have exhausted their supply of nuclear fuel and have exploded to make a supernova. Classes of these supernovae have pretty standard intrinsic luminosities, and so if you look at how bright it is on the sky, you can look for these effects of curvature of space-time. What's pictured here is the debris left over after the supernova, the material that has been ejected from it. This is big science, and it required lots of work by lots of people. Above is a photograph of Saul's group, another group based mainly in Cambridge, Massachusetts, and in Hawaii, or in Australia, Siding Springs, competed, have joined forces, they've grown other groups, and have obtained a bottom line. These measurements require Einstein's cosmological constant, that is to say, Lemaitre's dark energy. Let's not go into the details. There it is. There was a hypothesis introduced and a test, and it worked out. Now, of course, that's only one test, and you always have to be a little bit careful about what all of this might mean, but I guess I can't resist pointing out a wonderful historical situation. The evidence from the observations of these supernovae by Saul Perlmutter and his team, Brian Schmidt and his team, is that the universe at the present time the expansion of the universe these days is not slowing due to gravity, but rather speeding up due to the repulsive effect of Lemaitre's dark energy. That's a remarkable thing. It is just what de Sitter said in 1930. But of course, de Sitter was talking about something very different. In those days, people had the idea that originally dark energy and gravity were in balance. The balance broke, and the expansion started accelerating. The new picture, in the beginning, the universe was very dense, gravity was very strong, but it was expanding very rapidly, and dark energy had no particular effect. But as the universe expanded, gravity grew weaker because things are moving further apart, dark energy started to become important, and in this just so story, gravity is now becoming subdominant to the repulsive effect of gravity, and we have exactly the situation. What makes the universe expand or swell up? That is the lambda now. It didn't used to be, but it is now. Curious how things work out. Well, we need to check. We've got a positive check, but one check often doesn't convince. Possibly there's some systematic error. Just let's look around for other checks. Fortunately, we have them. And they deal with the evolution of this clustering of matter, which you see here, uniform on large scales, clumping on small scales. And in particular, with the evolution of this clustering, which is here illustrated below the distribution of galaxies in the universe as it is now out to a given limiting depth. I should remind you not to look at this S. That's the disk of our galaxy in this projection, curved and distorted greatly. That disk contains dust, and the dust obscures the light from distant galaxies. So that's an artifact of where we live. Here and here we have a good view out, and you see the uniformity on large scales, clustering on smaller scales. Above, the thermal radiation. I said earlier that we live in a universe that contains thermal radiation, smoothly distributed. It's not exactly smoothly distributed. The temperature varies across the sky by about a part in 100,000. Hot and cold spots now measured and shown above. This radiation was last appreciably disturbed by the irregular mass distribution, the theory says, when the universe was 1,000th its present size. You see, therefore, that we have a measure of how clustering has evolved as the universe has expanded. And that measure can be compared to our hypotheses to decide how the universe is behaving and whether or not our theories, including dark matter and dark energy, are on the right track. Here's an illustration. It's an old one. 1977, we were still using IBM punch cards, but never mind, it tells in a simple way the story. Start with a section of the universe that is close to uniform, place these mass points at random, follow the evolution of the universe as the whole universe expands, and of course this section expands through an expansion factor of 8, I think it was, and then 16. You can compare the distributions of points at the 3 times by expanding this plot to this size and shrinking this one to this size. So you've taken out the general expansion of the universe, and you see remaining that the universe used to be smooth and is growing clumpy. The universe is gravitationally unstable. A further point is illustrated in the bottom row. Here, the initial conditions are the same, but the mass of each particle is half that in the middle illustration. You notice the dramatic difference. The growth of clustering of matter depends on the mass of the universe. It's important to notice that small clumps are still visible because they happen fast. In a low-density universe, the expansion rate still soon becomes large compared to the effect of gravity, and the clustering is turned off. This, then, is a very important point to bear in mind. The universe is growing from bad to worse. Well, we all observed that. This evolution of the clustering depends on the properties of the universe. And if we can measure that evolution, we will have a handle on the properties of the universe. So here, this is getting a little turgid. I got to make several points. The first, I've already described. The departures from a uniform mass distribution grow. The universe is getting more messy. Galaxies are not forever. They didn't exist, nor did stars when the universe was very dense. They formed as the universe expanded, cooled, and mass fluctuations grew and coalesced into stars and galaxies. Second, the rate of this growth depends on the properties of the universe, things like the mass density, the dark energy density. Third, in the early universe, baryons are ionized by the hot radiation. The free electrons scatter the radiation, and the result is that baryons and radiation act like a fluid. That fluid is squishy. I had first thought I should bring along an example of a squishy fluid, a bowl of Jell-O. Would you imagine, please, a bowl of Jell-O and shake it? What do you see? You see oscillations. These oscillations have a definite property. Their wavelengths are fixed by the size of the bowl. I was persuaded that Jell-O tends to melt, and so I shouldn't do that. So I have instead brought along this musical instrument. Now, this is not going to be pretty, you'll understand, but it's making a very important point. So I make noise, and I make a sound. I change the boundary condition. I get a different sound. I send in noise. I select out of that noise certain tones. Mark is looking a little disgusted, but this is good science, you will agree. I am, in this device, favoring some wavelengths and suppressing others. In the expanding universe, there is a similar effect of boundary conditions. Musicians all understand boundary conditions. It's the top and bottom of the strings of the violin. It's the organ pipe's length of this sort. Boundary conditions in the expanding universe are, the universe started expanding from a uniform state. because it's unstable. Since it's fairly smooth now, it had to have been very smooth back then. Second, when the universe is expanded and cooled so the temperature is 3,000 degrees above absolute zero, when it was about 1,000th its present size, the matter, the baryons, plasma, recombined, made neutral atoms, and decoupled from the radiation. So you stop the oscillation. The result is that favored modes grow, disfavored modes are suppressed. Here is a photograph of some people who figure in all of this. On the left, Bob Dickey, my teacher, a great physicist and deeply admirable person. On the right, a close friend and colleague for many years, David Wilkinson. You'll see some more of him. In the middle, Jer Yu, my first graduate student at Princeton, now high in the ranks of the City University of Hong Kong. Jer Yu and I worked out this rigging and the choice of favored and disfavored modes, the analog of this musical instrument. Favored modes, disfavored modes. The effect of those favored and disfavored modes is to make favored and disfavored modes of distribution of the thermal radiation. This is a modern picture. This is what we now know, but we knew then, of course, that the favored and disfavored modes in the wavelengths for the matter make favored and disfavored modes for the disturbance of the distribution of the radiation. Apparent early on, therefore, that we'll learn a lot if we can measure these modes of oscillation. And so people started measuring. Here's David Wilkinson again with another friend and colleague, Bruce Partridge, on the left. The clipping is from a newspaper. I do not wish to comment on the caption, but I can't resist drawing your attention to the handwritten note on the side, Denver Post, July 24th, 1967. I can't read it. Oh, Harold, of course. Harold and Thelma Wilkinson happened upon this article at the Brass Lantern Post restaurant in Kimball, Nebraska, while traveling. Dave's mom and dad were made proud. They are setting after the great goal of discovering these irregularities in the radiation distribution, which they'll compare to the theory and see whether our hypotheses are in line with reality. Here is David again in the 70s. I forgot to remind you, notice the width of the tie. Okay, this is 60s. Notice the length of the hair. David on the right, Peter Salson, a graduate student in the middle, and Ed Cheng, another graduate student on the left. And an instrument that would be taken up in a balloon to look for this variation in the temperature of the radiation across the sky that ought to be there and ought to teach us about how the universe is behaving. Here is a project report for a satellite that became COBE. We mentioned yesterday that this guy was project scientist, and he is pictured in the next transparency. This is John Mather. He received the Nobel Prize in Physics just a few weeks ago. Here is another PI for the experiment I'm going to be describing in a moment, George Smoot, who you've just seen, a Nobel Prize in Physics just a few weeks ago. The third PI, Mike Hauser, another good friend, and he deserves a Nobel Prize too for magnificent work, but you can't do it. You can't have them all. David Wilkinson, Ed Cheng you saw, and a cast of thousands. Not exactly big science, but a hard-working group. And here is an illustration of the situation just before the satellite that these people built, tested, and flew, and used for observations was launched. 1990, an article by Joe Silk, who was a professor of astronomy here, now the professor of astronomy in Oxford in England. And I wrote, you can't read anything on here, you're just supposed to notice that it's a pretty full page. The columns are sets of hypotheses about the nature of the universe. Some have dark matter, some don't. The rows are observations. And the entries are each are grades for how well the hypothesis fits the observation. The details are of interest entirely and only to historians of science. Some of these things are woefully misconceived, others more or less on the mark, I guess. But that's not the point. We needed the help of the observations to sort out all of these possibilities, and we got them. Upper left, the red symbols are the COBE results for which George Smoot received a Nobel Prize as PI for this marvelous experiment. Down below, the map showing the variations of the temperature across the sky. You understand the mean has been subtracted. These are variations of a part in 100,000. You notice to the right, people had jumped on this and were trying very hard to look at what the anisotropy is, the fluctuations across the sky on smaller scales. Without much success. Nothing was believable. You might also be able to see blue lines running through. Those are different theories based on different of the hypotheses in that last chart. You can see how good measurements are going to straighten this out. Already, COBE pointed us in the right direction. The observations by Smoot and al. Pointed us in the direction of one of those sets of hypotheses in that last slide, the now very successful cold dark matter, dark energy theory. So let us look at the next step. It's obvious we got to do even better than COBE. You know it can be done, now do it. This is a proposal for a next generation experiment. It was called MAP, Microwave Anisotropy Probe. I couldn't resist showing you this memo dated 1991, even before COBE had its first results. The result of a proposal by David Wilkinson to build a satellite to do even better than COBE. Involved in this first project were Ed Wallach, then a graduate student, Norm Jurasik, and Lyman Page, then instructors at Princeton, along with David Wilkinson. They went down to Washington, D.C. They talked to NASA and to Martin Marietta, one of the Beltway bandits, but an expert on the technology these people would use. And I just wanted to point out the opening statement. They seem to like the science. Oh my God, this is spectacular science. And indeed, people liked it. The proposal was submitted, the group formed, and here is a group photograph. David Wilkinson is seated on the far left. You can see Lyman Page seated with the Scandinavian sweater. Above to the right, Ed Wallach, whose name you saw earlier. Norm Jurasik, far right, standing, and others. Licha Verde, now at University of Pennsylvania. Pyrrhus, now at University of Chicago, if I remember right. And some results. Just spectacular. This is, again, the texture of our universe, but looked at in a different way. The results of the disturbance to this thermal radiation by the irregularity in the mass distribution back when the density of the universe was very much higher and it was able to interact with radiation. I just can't resist the comparison between what people were doing in 1967 and what they got. There is progress. And an illustration of, I should have remembered to show you, you've seen this before. And now I wish to boast a bit. Notice how wonderfully well the theory follows the measurements. Noisy in here. They've even improved since this transparency was made just a year ago, but less than a year ago. But that's okay. It's spectacular agreement. I wanted to show you, though, an example of yet another test. Take the theory as it now is assumed to be, and notice that we have this ringing that favors discrete modes of variation of the mass distribution. And notice that if those modes are evenly placed, it will have the implication that there's a correlation between the mass fluctuation here and the mass fluctuation over here at a rather well-defined length, about 400 million light years. Go measure that correlation, and there it is. It showed up. I point this to you only as an illustration of the situation illustrated on this exceedingly busy slide. Now here's the situation. We have lots of postulates. In those postulates, for example, that there is dark matter, we have to say how much. Dark energy, baryons, how much of each? Initial conditions, do we really have them right? All of these parameters can be adjusted so as to fit this curve. But you don't have complete freedom to adjust. First, you can only adjust this curve so much to fit the observations, and then second, we have lots of other checks on what is going on. I showed you one. There's a long list of others, and the situation now is very clear and straightforward. Clear and straightforward. We have redundantly and overwhelmingly tested this set of hypotheses, this just so story. It has passed many tests. We've got to accept this is a good approximation to reality. No one should ever tell you that this is reality, this is the absolute truth, but it is a very good approximation. That, of course, is all we can ever hope to ask. So I bring now a summary pair of slides just to comment on the way things have gone. Up above, this dream of testing our ideas of curved space-time and of the effect in this curved space-time of dark energy. We have, one may say here, 3 generations illustrated. First generation, 1930s. Georges Lemaitre, a wonderful theory. Edwin Hubble, a wonderful telescope that may be able to test the theory. 30 years later, in the early 1960s, Alan Sandage, the telescope has been built, let's use it. Let's learn how to measure these galaxies and make these tests. Another 30 years after that, Saul Perlmutter and co-conspirators, let's do it even better by looking at supernovae, and let's succeed, and at last, success. Through 3 generations, one at last succeeded in making the measurement. These people are tenacious, they're tough, and they succeed sometimes. Zwicky, he disapproved of many things. Actually, he was always polite to me, but you had to be careful. I don't know whether he would approve of the way we are treating his dark matter, but there it is. This story would not work if the dark matter he noted and if the dark matter that Vera Rubin saw had not been present. Of course, you only knew that the dark matter had to be there because of these tests, including David Wilkinson in the 1967s learning how to make these measurements. This group, and here is George again, longer hair there. Different times, yes. Your tie is gone now. In fact, you didn't have it there. Made these measurements and showed us the way the world really is. And some more thoughts. We have open problems. Although we have brilliant successes in checking our ideas about the curvature of space-time, we have deep problems. We needed to postulate dark matter. We got to find it. And people are working hard on it. We have this ridiculous dark energy that great authorities were willing to assure you is absurd. Einstein, Pauli. But yet, gee, it should be there. And yes, it should be there. And my goodness, it's there. But what is it? We don't know. We can only leave it to groups such as those on the upper right to find out by getting new hints, test new hypotheses, and finally find some success. In short, cosmology has had a brilliant run, but I think it's by no means over. There are lots of open questions for the next generation. Thank you.
A very elementary question. What is the difference between dark matter and dark energy?
It's elementary, but really, really important. Dark matter has no pressure to speak of. It's able to cluster very easily. Dark energy has so much pressure, it's almost totally incapable of clustering. Furthermore, the pressure has a bad sign, it's negative. It's material with a bizarre set of properties. It's called dark energy in part because it just has the properties you would expect for zero-point energy from all of the fields of standard physics, except for the wrong value. It acts like an energy, but to give it that name is somewhat misleading. It suggests we know what it is. That's quite wrong. Ask the question again in another generation, you may get a better answer.
Yesterday, you suggested that we should perhaps write to our congressman or somebody to support that idea that basic science is useful. And it occurred to me it might be useful to have a couple of examples, and maybe more. I'd like to give 2 examples of basic science which have turned out to be useful. If you use a GPS system to drive around in your car, it won't work without general relativity corrections. I don't remember what the error is. Perhaps someone knows here in the room, but it's a big error. A second example is if you go in for what's called an MRI scanner. They took the nuclei out of nuclear magnetic resonance imaging, and that's works because the nucleus, like a proton, is spinning around like it has angular momentum like a top with a magnet attached. And those were basic things which were discovered at the beginning of the last century, and it took a bit of computers to get the magnetic resonance imaging to work. What could you draw from your experience, not necessarily from cosmology, but what would you urge for people to put in their letters to the congressman?
I'm not sure if I would put it in a letter to the congressman, but the example I often use, your examples are excellent, and I may steal them, but the one I use is a cell phone. Now, I am not at all convinced that cell phones are an entirely unmixed blessing. But I am deeply admiring of the fact that in that little handheld device, we see evidence of the ability of engineers to control the behavior of molecules, to make that liquid crystal display, to control crystals and electrons, to move around and do logic, and to remember my phone number and dial it. The ability of electromagnetic fields to control molecules and electrons and to send and receive signals. It's spectacular. And where would faith-based science have taken cell phones?